All software will be self-evolving software very soon. This is a new paper from a team out of Stanford, MIT, and Crafton, and it's called Meta Harness, end-to-end optimization of model harnesses. If you've been following the AI industry at all, if you've watched this channel at all recently, I have been talking about agentic harnesses a ton. What is a harness? It is basically the traditional code that is wrapped around a model like Claude, like GPT-5.4, like Gemini, that tells it how to operate, that allows it to store memories, search through text, write code, execute code, and so much more. It is what makes things like Claude Code, Cursor, Factory, and so many other agentic harnesses so special. When you type in a prompt in Cursor, it can run for hours on end, and that's all because of the harness. I'm going to explain all of this in detail, but now imagine if the harness itself can actually self-improve. Typically, they're written by hand, by a human, they're run and they're evolved over time, but they're not self-evolved. And let's pause there for a moment and talk about Andrej Karpathy's auto research project, which absolutely blew up in the last couple weeks. Already at 61,000 stars. Basically what it does is it allows a model like Claude to propose a series of experiments to run overnight, self-improving its ability to train a GPT-2 level model. If all of this sounds very foreign, just think of it like this. It's AI training itself. It is looking at what worked, proposing new experiments on how to do those things better, and then continuously doing that all night long. And since this project came out, there have been a number of projects that are very similar, looking to essentially self-evolve, self-improve different pieces of software. And now we actually have the harness itself that is able to self-improve. So cool. Let's get into the details. So here's the paper. They already published the paper and they open source the code so you can use it right now. I'm going to drop all of these links in the description below. All right, let me give you the gist of what we're going to talk about. The performance of large language model systems depends not only on model weights, but also on their harness. The harness being the code that determines what information to store, retrieve, and present to the model. The harness is just as important as the model weights. Now, if this is confusing, let me just explain quickly. The model itself, when you hear GPT 5.4, when you hear Opus 4.6, we're just talking about the model weights. When the frontier labs do these huge pre-training runs, they're basically baking what eventually becomes the weights of the model. And the model weights are really, really good at predicting the next token or the next word in a series of words. That is really all they're doing. But they become very special when you wrap them in a harness. When you say, hey, next time you're predicting the next word, maybe you should also look at the memory over here. Or maybe you should write some code and then execute it over there. And I'll give you an environment for that. And you can save files over here. There's so much you can do with an agentic harness, and the models themselves, the weights, are incredibly powerful already. They are incredibly intelligent. I've been saying this for a while. The models are good enough to reach AGI today. All we need to do is build out the harness. I used to call it scaffolding, but now it's called a harness suddenly, to make them really good. So then they introduced Meta Harness, which is an outer loop, so around the agentic harness system that searches over harness code for LLM applications. All right, let's get into the details of Meta Harness now. Changing the harness around a fixed large language model, so just the weights, can produce a 6x performance gap on the same benchmark. Harnesses are everything. The models are so good at this point, but that's just raw intelligence. That's like the engine of a car. But the engine of a car is not enough to get you from point A to point B. You need seats and you need a steering wheel and you need a way to deliver all of that power that's coming out of the engine to the tires and the tires to the road. So the harness, the code that determines what to store, retrieve, and show to the model, often matters as much as the model itself. Yes, this is called harness engineering, and the best frontier labs are making their own harnesses. And there's a bunch of other companies that make their own harnesses that are fantastic. And I'll talk about a few of them today, but you probably have heard about most of them. But despite its importance, harness engineering remains largely manual. And you know what else needs to be self-evolving? Your skills. And that's why I'm excited to tell you about the sponsor of today's video, HubSpot. I know a lot of you are trying to keep up with how fast AI is moving, and you want to actually learn about these tools, not just read about them. Claude Cowork just came out and lets you automate huge portions of your workload. And so I suggest you check out the Claude Cowork Stack, 12 prompts to replace a week of work. This is the guide to understanding AI agents and how they actually work in practice. It covers the different ways to use Claude Cowork and specific walkthroughs about how to get the most out of it. You'll understand how to give your Claude Cowork agent access to hundreds of files and to let it do deep analysis, pattern recognition, run autonomous tasks in the background, and all without having to babysit it. You will get real deliverables from Claude Cowork like spreadsheets, presentations, and reports, instead of just chat responses. I personally found the section about background processing and real file creation to be particularly helpful because background processing is what AI agents look like in 2026. So this ebook was made by HubSpot. They're giving it to you for free. Shout out to HubSpot once more. They've been a fantastic partner. So go download this ebook. It is a great resource. Plus they're a great sponsor. It helps the channel. Now back to the video. And so the authors of the paper asked, can harness engineering be automated? And it turns out it can. So check this out. A natural starting point is recent work on text optimization. When they say starting point, they mean how can we experiment on a harness made for a kind of narrow use case, and this is text optimization. Harness engineering also involves iteratively improving text and code artifacts using feedback from prior attempts. So the actual harness itself is executing that learning pattern, but the harness is not doing it itself, if that makes sense. Let's keep going. So these methods are poorly matched to harness engineering because they typically operate with short horizon or heavily compressed feedback. Some condition only on the current candidate. Others rely primarily on scalar scores. So just think, 0 to 1 scores. But a 0 to 1 score is not really good for what they're describing here. It doesn't really work. The problem is harnesses are incredibly complex. They include so many different factors, so many different success signals that boiling them all down to a single score like 0.4, 0.8 makes it very difficult for us to understand how to improve or which parts of the harness we should improve based on that score. So harnesses act over long horizons. A single choice about what to store, when to retrieve it, or how to present it can affect behavior many reasoning steps later. Compressed feedback, so that means, okay, let's figure out what happens, let's summarize it using a model, and then feed that summary into this experimentation loop that we're trying to do. It doesn't really work. Compressed feedback often removes the information needed to trace downstream failures to earlier harness decisions. Across the task studied by several representative text optimizers, the available context per optimization step ranges from only 100 to 30,000 tokens. Basically, they're trying to boil down everything that comes in a harness, which can be millions and millions and millions of tokens, down to a few tens of thousands of tokens to try to figure out what happened. And obviously, you lose a lot of quality. You lose a lot of the signal doing that. So it's not a good approach. And here's an important concept we're going to go over a few times during this paper. Work on retrieval and memory augmented language models, meaning we have this large amount of memory, this large amount of data. What should I choose to give the model? That's all it means. Suggests that useful context should often be accessed adaptively rather than monolithically packed into a single prompt. And there are multiple reasons for that. But first, what does that mean? That means let the model decide what it needs. Don't try to figure out what it needs. Don't try to pack everything into a single prompt up front and give it to the model. Just say, hey, here's what you have available. You choose. And it seems more often than not, that is the right approach. All right, so how does Meta Harness actually work? Well, it has a proposer and it is a coding agent, a language model-based system that can invoke developer tools and modify code. Basically, basically a harness around a model. And the choice of using a coding agent versus a raw LLM was deliberate and makes a ton of sense. Let me show you. The choice of coding agent rather than raw LLM matters because the amount of experience quickly exceeds context limits. Meaning, of all the code necessary to write a harness, as I said earlier, you can't fit it all into the context window. So you have to give the model and the harness around the model the ability to choose which parts of the harness it's going to read and understand as part of its experiments. The proposer must decide what to inspect and validate edits through direct interaction with the code base. So this is very similar. If you're doing any kind of agentic coding right now, you're probably familiar with how to visualize what I'm talking about right now. So for example, this is Cursor. I said, review the entire code base for code issues, user confusion, and so on. And what it did is it read the entire code base, but not all at once. It looked at the different files in the code base. It looked at the different methods, decided where it should gather more information. And that's what you're seeing here. And that's exactly what the coding agent in MetaHarness is doing, the proposer. And now we get the full history of all the harnesses. So imagine this, you have a harness, you test it, you make changes to it, and then you test it again. And now you have 2 versions of the harness. And now imagine you do that 10 different times. And so if every harness is 1 million tokens and you do that 10 times, you now have to reason over 10 million tokens, which is not possible based on current LLM context windows. So instead, we give it everything and we give it the tools to know how to look and find what it needs. And it works exactly like that. So for previous candidate harnesses, the file system stores the source code, evaluation scores, and execution traces, which the proposer retrieves via standard operations such as grep and cat, rather than ingesting them as a single prompt. So it is very meta, as the name suggests. So they ran a bunch of tests. We evaluate MetaHarness on text classification, great, on retrieval augmented math reasoning, which I'll explain when we get there, and on terminal bench 2, which is the benchmark testing how these harnesses operate terminals. All right, but MetaHarness didn't come out of nowhere. They built on top of a lot of ideas and concepts that are floating around the AI industry right now, and let me point those out. So here's the related work. So first, external memory and adaptive access, retrieval, augmented generation, interleaved retrieval and reasoning, memory-based agents, or recursive language models are mechanisms for adaptive access to external context. And they leveraged a lot of these concepts in the MetaHarness. Executable code search. MetaHarness searches over domain-specific harnesses, including prompt construction, retrieval, and state update strategies that reset between tasks. Its outer loop is deliberately minimal, which I really like. Minimal is good. Instead of relying on a fixed scaffold, an archive of prior discoveries, or a persistent memory mechanism, it gives the proposer unrestricted file system access to prior experience. Again, let the model choose what it needs. It also gains inspiration from other systems that improve itself. One of the ones that I want to point out is Alpha Evolve by Google, which figured out ways to optimize Google's own systems architecture and actually figured out a faster way to do matrix multiplication, which was the first time we figured out a faster way in like 50 years. So this self-improving loop is incredibly powerful. So how does it actually work? At a high level, it repeatedly proposes, evaluates, and logs new harnesses. Very similar to how auto research by Karpathy worked, trying to figure out a faster way to build a GPT-2 model. The goal is simple: find the harness that makes the underlying model perform best on the target task distribution. So here's the loop. MetaHarness uses a single coding agent proposer with access to a growing file system that serves as its feedback channel. Here, the coding agent is a language-based model system that can invoke developer tools and modify code. MetaHarness delegates diagnosis and proposal to the coding agent itself. It decides which prior artifact to inspect, which failure modes to address, and whether to make a local edit or a more substantial rewrite. Why did they do this? Why are they letting another harness try to figure out how to improve the harness itself. It is just so meta and it's so recursive. And that's exactly why. As the core models get better, the LLMs themselves, as the harnesses get better, as the meta harness gets better, these multiple layers of self-improving, recursively self-improving, I should say, factors stack on top of each other. The success rate and the velocity to success increases dramatically very quickly. So each evaluated harness contributes a directory containing its source code, scores, and execution traces. So that's stuff like prompts, tool calls, model outputs, and state updates. The proposer is free to inspect any prior harness, so it is not just told only inspect the best performing ones. It can inspect any of them, even the low performing ones, because you can avoid local maxima that way. And while it's proposing new ones. So you give it a fixed number of iterations and perform a final test set evaluation on the Pareto frontier. This simplicity is deliberate. Listen to this. By leaving diagnosis and edit decisions to the proposer rather than hard coding such heuristics, MetaHarness can improve automatically as coding agents become more capable. So the target for improvement can improve the improver, which then improves back the target for improvement. So now MetaHarness reads everything. It's looking at the code, the prompts, the tool calls, the output, the terminal output, everything. And it's determining, what should we change? Should we make a little change? Should we make a big change? Then it puts forth a new harness, and then they test against that harness, and they continuously do that over time. And interestingly enough, I'm a big fan of Opus 4.6, and it seems like the authors of this paper are as well. So in our experiments, the proposer, they chose Claude Code with Opus 4.6. Now, personally, I use Cursor with Opus 4.6, but a lot of people I know are using Claude Code. As I mentioned earlier, they have 3 experiments that they're running. One on text classification, one on math reasoning, and one on agentic coding. And they compete against 2 different things. One, human design strategies. So if a human wrote the harness themselves, that would count there. And program search methods. These methods search over candidate harnesses using feedback and reward signals, but are designed for smaller scale settings than harness engineering. So basically kind of self-improving code, but not meant for this level of self-improving code. All right, so let's look at some of the initial results. So first we have the online text classification benchmark. And what that is meant to do is take text and, exactly what it sounds like, classify it. And it's not just the model, the raw LLM that does that, it is also the harness around it. So we have 0 shot. So that literally just means put the text in the LLM and say, how do you classify it? And it takes 0 context and does okay. All right, so for USPTO, which is the Patent Trade Office, I believe, it gets a 12. On the symptoms to disease, which is a medical text benchmark, we have 63.2, still really good. And then the law benchmark, a 7, which compared to the other results is very bad. We have few shot with 8 examples, few shot with 32 examples, and few shot with all examples. And you can see they get a little bit better over time. So the more examples you give it, the better it does. We all knew that. This is early prompt engineering learnings. Next, we compare against MCE and ACE, which is basically kind of the next evolution of prompt engineering. MCE is meta context engineering, and it allows the model to build and curate a library of natural language skills to help it with its task. And then ACE, which is agentic context engineering, which basically allows the model to reflect on what it's learned over time. So as we see for the USPTO, ACE actually did best, although the meta harness down here did pretty well at 14. For the S2D, the meta harness did really well, going 4 points above the second place of MCE. And then for law, it absolutely dominated. The highest score being a 29 with few shot and ACE, and the meta harness coming in at 45, a massive, massive improvement. And the average overall, it is the best. It scored a 48. Second place, 40.9 with ACE. Not only was it better, but it also used far fewer tokens. Look at this. This is the context usage. So 0 shot, few shot, all the way up. ACE and MCE, 28.5 and 50.8 on their context. 11.4 for the Meta harness. So it is far cheaper and just as good, if not better, on most cases. So Meta harness matches the best prior text optimizers, OpenEvolve, TTT Discover, with 10x fewer full evaluations, and its final accuracy surpasses theirs by more than 10 points. So these are literal optimizers that were built for text classification, and it still beat it. And the nice thing about Meta harness is it doesn't go in with any preconceived notions. It just says, okay, let's start testing and see what works. A human doesn't have to curate the experiments or decide what to change in future experiments. It's all automated. And so it's really just limited by how many tokens can we throw at it and how fast are those tokens. And so let's look at one more thing, because this is super interesting. The Meta harness median score against the other best-in-class harnesses, state-of-the-art harnesses for this task, it gets a 50 as compared to a 39.1. Now, the best score for all of the other ones is 45.6. The median score for the Meta harness is higher than the best score from all the others. And of course, the best score for Meta harness, 56.7. So you can see this is not just luck. The Meta harness, the auto research, the self-improving way of doing things is the best. So then they thought, okay, are we overfitting? Are we making the harness that is just so good at this one task and maybe not so good at most other tasks? Well, it turns out no. They actually took the harness that they built based on those 3 tasks and generalized it out to 9 other data sets that the harness had never seen. And more often than not, it won. And on average, it was the highest score by 3 points, 73.1 versus the second highest score with ACE, 70.2. And it was relatively inexpensive, definitely more expensive than Few Shot, but less expensive than ACE. And then they thought, what if we applied this to mathematical reasoning? What if we put our Meta harness up against the IMO, International Math Olympiads? That is, mid last year, all of the frontier labs were competing in the IMO, showing that their models with a ton of harness around them can perform incredibly well in that competition. That is the frontier of math, the hardest math problems given as a competition. And here's what they found. The discovered Meta harness retrieval strategy improves reasoning on these IMO level problems across all 5 held out models with a 4.7 point average gain over no retriever. But how does that even make sense? Why would retrieving past memory or past context help with a new math problem? Well, they explain. There is a good reason to expect retrieval to help mathematical reasoning in principle because solutions often share reusable proof patterns. So that's it. They said, well, what worked for the last one? Maybe we can use part of that proof for our current problem. So very interesting. All right, last and my favorite, terminal bench. This is the benchmark that tests a model or a harness's ability to interact with a terminal across long horizon, difficult tasks to be done via terminal. So Terminal Bench 2 evaluates LLM agents on 89 challenging tasks that require long horizon, fully autonomous execution under complex dependencies and substantial domain knowledge. They use this benchmark as a discovery problem. The goal to discover a harness configuration that improves performance on a hard, publicly contested benchmark. So look at all of these. You've probably heard of some of them. Claude Code, obviously. Droid, one of my favorite. And so what are the results? We have Claude Opus 4.6 and Claude Haiku 4.5. These are the 2 core base models that they tested against. And remember, this is against the Terminal Bench benchmark. So Meta harness on Opus 4.6, this is the frontier model on the market today, it scored a 76.4, higher than every other benchmark that has been handwritten with the exception of Forge Code. So remember, Meta harness wasn't really written at all. It was just evolved from the Meta harness framework. Then for Haiku 4.5, it did better than all of them, 37.6 versus second place Goose, 35.5. So just letting the model figure out how to build its own harness seems to be the way. And this seems to all tie back into something called the bitter lesson. I know it's not a direct analogy, but it feels close to me. And so the bitter lesson shows that handwritten heuristics by humans, basically patterns described by humans, never beat just end-to-end neural networks, the AI itself learning those heuristics on the fly. And so the most prominent example of the bitter lesson is Tesla's full self-driving. For a long time, it used a combination of neural nets and handwritten code. If you see a stop sign, you better stop. But over time, as the neural net got bigger and bigger, what they figured out, and they swapped it all out for end-to-end neural nets one day, is that those neural nets will figure out those heuristics itself. And that's always the best way. AI figuring out what to do will always beat humans telling it what to do. Remember that. That's going to pop up in our lives a lot over the coming years. And so right now, the harnesses are written by humans. But should they be? Obviously not. If you're writing any code, if you're writing any automations yourself, why can't we extrapolate this to say all code should be self-improving? All code needs its own meta harness. Why not? We've already seen a lot of examples. We've seen the founder of Shopify improve a code library significantly that hadn't been touched in years. And it just let Karpathy's auto research just iterate on it and figure out how to improve it. And it had massive gains from just letting AI write it and rewrite it and rewrite it. And so a lot of the token usage in the future is going to come from just letting the tokens burn and iterating as much as we can on these problems. So I found this paper to be absolutely fascinating. And I really think self-evolving software, self-improving software is going to be such a big presence in artificial intelligence in the coming years. We're already seeing it. We're starting to see the frontier labs put out models that were trained by previous models. And we're going to start to see harnesses being built by previous harnesses. And then we're going to see all software just being built by previous software. And it is so awesome to watch. It is so fascinating, and it is hard to keep up at times. But if you follow me here, I will help you keep up as best I can. If you enjoyed this video, please consider giving a like and subscribe, and I'll see you in the next one.